Alrighty. Let's start reviewing some sigma algebra stuff. So, theorem 1.1, for the pi system C and lambda system D in a space S, we have that if C is a subset of D, then the sigma algebra, smallest sigma algebra containing C, is a subset of D. Okay, that seems like it's probably useful later. I don't really need this right now. So last time when I was working on this, I was on lemma 1.2. So here we have that the Borel sigma algebra of a countable product of topological spaces is equal to the countable product of the Borel sigma algebras. All right, so let's go back and remember what exactly these two things mean. For any class of spaces S, T of S, we define the it's a class of all collections S sub T using a bit of theory of axiom of choice there, and we often write the product space like so, blah 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 blah. Okay, now assume that each space S sub T is equipped with a sigma field S sub T. Then this infinite product is generated by all the one-dimensional cylinder sets. So S sub T are each sigma fields, and basically what we get is we get S1 cross S2 cross dot dot dot, and then at some point Sn cross, and this is n plus 1 cross Sn plus 2 cross dot dot dot, and that is an element in Borel S n plus 1. And then we take this set and we consider the smallest space of all. Oops. Still getting used to how this all works. Put you down there. So the space of, so then we take the sigma algebra of, we'll call this Q, is everything that looks like this, and this will be sigma of Q. All right, and then so the product, countable product of topological spaces. So if we have topological spaces, we'll call them B1 cross dot dot dot. Then an element of this looks like, I believe it is any, so it is equivalent to pointwise convergence. So the basis of this looks like B1 cross B2 cross, and then, some number of these, A4 cross B5 cross A6, some finite number of these are, so this would be an element of B3. Yeah. No, this is fine. We'll just pretend there's a topology over this. So this will be in T3, let's say. This one is in T4. This one is in T whatever. So this looks like a rectangle where all but finitely many of the dimensions are just the entire space. All right. So that's what this looks like. So thus, for a countable product of separable metric spaces, separable is important here. I guess that, yeah, so the countable basis is important. The product and Borel sigma fields agree. In particular, that holds. That's easy to believe. This first statement here, you can just cook up a basis, go back and forth between these. There's a sigma field by all rectangles, blah, blah, blah. All right. All right, so, but for a countable product, take C1, we want to show that the smallest sigma algebra containing C1 is equal to the smallest sigma algebra containing C2, where C1 is the class of open sets in, yeah. Okay, so that's what we were talking about before. And C2 is the class of cylinder sets of this. Okay, so we know that sigma of C2, is equal to this. That's fine. That's the basis. Okay. And C1 is a class of open sets. Yes. It almost seems like it should be really obvious. All right, can be shown that C1, whereas a class of open sets in S1, blah, blah, blah. So, and C2 is the class of cylinder sets of the form of that. Okay. So, basically, I just need to show that, yeah, okay. So basically what I need to show is that, I need to show that C1 is a subset of sigma of C2. C2 is a subset of sigma of C1. And then I think that's fine. All right. Now let C be the subclass of such cylinder sets with BK open in S. Okay, so a cylinder set means finitely many. Let B, okay, so let's C be the subclass of such cylinder sets with B open in SK. So that's an element. All right, so let's just write a quick reminder here. Whoops. I need to turn that off at some point. So the product, okay, product topology. So cross T equals 1 to infinity S sub T. Oh, we just assume that it's going, so topology is equal to sigma all but finitely many are all but finitely many are entire space, and rest are open sets. So that's topological, and then so this is the product type. Topological sigma algebra. Say sigma all but one entry our entire space. And that one entry is from whatever sigma of, well, b sub st, right? So that entry. Okay. So C1 here is blah, blah, blah. Okay, and cylinder sets. Okay, so there's sigma algebra is the one with cylinder sets. Hard to keep this all in my mind. So let's see here. So C1 and C1 is a class of open sets. Okay, so C1. This is C1. This is C2, just to keep these. So C1 is the Borel set of the topological product. C2 is the topological product, or sorry, the sigma field product of Borel sigma algebras. Okay. So this is all fine. Now let C be the subclass of such cylinder sets with BK open K. Okay, so we're just, looks like we're just fixing an index and say, let's look at all of these. Then C is a topological base in S, should probably be S sub K. Is that right? Oh yeah, so C is, yeah, that's fine. I don't quite see how C1 is different. Ah, I see. Okay. So they're basically just changing the finitely many to 1. That's okay. So this is related to C. And C is a topological base in S. Okay. This is fine since C is separable. Every set in C1 is a countable union of sets in C. Okay. This makes sense. Hence, C1 is a subset of sigma and C. I mean, C. Okay. Every set in C1 is a countable union of sets in C. Am I crazy? It seems like C should be a subset of C1, like proper. Ah, okay, I see. So C, okay. Yes, that's true. But because we can do finite countably many unions, C1 is indeed, so every element of C1 looks like countably many unions of elements of C, and that's contained in the sigma algebra. So this is true. Furthermore, open sets in SK generate BSK open sets in SK generate BSK. I see. So we just fix. Okay, so we. Generally, C lies in both of these. Huh. That's a weird proof. So basically, we show that we can take an element of each of these bases for the different types of space and show that we can get the element of the other one. Somehow, I feel like this should be able to be written more clearly, but whatever. Okay, moving on. Every point mapping f of s to t induces a set mapping. Okay, so this is just defining inverses in the opposite direction given by f to the negative 1 of b are those elements in S such that f of s lies in B. B is a subset of T. Right, okay, yeah. Going from T, going backwards, T to S. All right. Note that f to negative 1 and preserves basic set operations in the sense that these hold. Again, this is like one of the bizarre properties. It's easy to verify all of this. Just like power through the set theory definitions. But somehow it's weird that the inverse is the function that's well behaved, whereas the forward direction is not so well behaved. I really don't. Still, I mean, I get it, but it's still there's something still kind of strange about all that. Okay. Show that f to the negative 1 also preserves sigma fields. We show that, okay, for convenience. I'm not going to prove this one. Probably skip the proof. Induce sigma fields for any mapping f between measurable spaces. Okay. T to the negative 1. Aha, this is how we're going to eventually use this to get to induced sigma fields from a random variable. We can just skim this. We have a sequence in S prime. Let's see here. Blah, blah, blah. F goes from, let's just write it down to help remember. F is a function from S to T. And if we have, all right, so S prime is the sigma field induced by F. And there exists some sets B1, blah, blah, blah. I mean, it's, okay. It's just this, it just follows directly from the set operation deals. what's the second one here? T prime. B subset of T such that, That's so weird. Okay, so S prime is the one that gets induced by T. So yeah, it's not assuming that F is measurable, so this S prime can be bizarre. You need measurability. T, yeah, kind of like, it's a bit of a weird one. Let B1 through B in T prime, so that each of these lie in S. Okay, I guess that's fine. So you could even have like, B and B prime such that F to the negative 1 of B is equal to F to the negative 1 B prime, where these guys aren't equal even. Something weird could happen there. Okay, which all belong to S, thus the union and the intersection of line T. Well, whatever, it seems fine. All right. For any measurable spaces S and T, a mapping F of S to T is said to be S/T measurable. Analogy, yeah. I mean, this is all stuff that I know. So maybe I can kind of go through it quickly. If F to the negative 1 of T is a subset of S, yep, this is fine. All right, let F be a mapping between measurable spaces. Let's go to line 1.4. Any mapping could be bizarre. Okay, so this C is just everything with sigma of C. Okay, and let C be a subset of. Okay, so this is basically like a basis. I guess might be going back to that pi lambda stuff. Let F be a mapping between measurable spaces. S and T, and let C be a subset of 2 of the T, such that it is a basis for the sigma algebra. Then F, so ST measurable. I see. Okay. ST measurable means from S to T. Is if and only if F to the negative 1 of C, your basis, is a subset of S. Yeah, that makes sense. Everything's preserved through inverses nicely, so we don't really need to check this. Let's keep going. Continuity and measurability. For a map F between topological spaces S and T with Borel sigma fields, if F is continuous, then it's measurable. Yeah, measurability is weaker than continuity. It's kind of like continuity. It's like continuous is a bit like being almost everywhere constant, and then measurable is like being almost everywhere continuous. Like if you, continuous means that if, continuous means, we can zoom in really close. So we'll just pretend we zoom into this. then it looks like that. Looks flat. And measurable means that it is almost continuous, but in like a bizarre way. This is from Lucen's theorem, I think. Let me see if I just look this up real quick. Lucen, yeah. States that almost everywhere, general form, radon measure second countable topological space. Formally measurable functions into spaces with countable base may be approximated by continuous functions on an arbitrarily large portion of their domain. Yeah, so you can you have a function that's measurable. We'll just pretend it's really nasty, and basically you can sort of just like, if you just ignore large enough portions of this space, then it looks continuous. But you can't look at the whole space. Okay. But you need some regularity conditions. Okie dokie. We insert a result about subspace topologies and sigma fields needed in chapter 23. I have no plan on getting there, but let's take a look. Subspaces. So S sub rho is metric, gives us T. You can just say, well, whatever. S rho is good enough. Now let's write S rho T. I don't like how they're mixing S and T now, though. Blah, blah, blah. And Borel sigma field S. Okay, right. That's fine. And let A be a subset of S. Okay. It's just some element of S, or basically like an element of the topology or the Borel sigma field. But it could be nasty. Doesn't necessarily belong to either of those. Then the induced topology and Borel sigma field and A rho are given by induced topology, Borel sigma field. All right. So the Borel sigma field is known. I see. Okay. Yeah, so I guess the subspace sigma field. Yeah. I don't know. This is standard stuff. I don't particularly care about the subspace topology or sigma field. Why would this even be hard, though? T sub A is equal. It seems like subspace topology. See, I almost think that's the definition. Subspace topology. Given a topological space and subset, the subspace topology of X is defined by. Yeah. Looking at this on Wikipedia, this literally looks like the definition. With the natural embedding, I see. I don't get this. I see. I think T sub A is a definition. Right, I mean, that makes sense. T sub A is a definition. S sub A you get from T sub A, and it's showing that indeed all you do is just intersect everything with A, and it all just works out in the end. Not surprising, but something you do need to show at some point. wonder if I should make this a little bit quieter. Let's turn down this gain a little bit, turning down the gain. Try this, testing, 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 testing. Okay, so that's getting quieter. Hello, hello, testing. All right, that's a little too loud. All right, so we can do this. Okay. This seems fine. As with continuity, even measurability is preserved. Oh, there we go. All right. Testing, testing. All right, this is fine. Even, I can still hear a hiss though. As with continuity, get a little bit quieter. As with continuity, even measurability is preserved by composition. Composition, F, I see, okay. Blah, blah, blah. That's fine. This is all basic. For many results in probability theory, it is convenient to first give a proof for the real line, then extend to more general spaces. Say that a measurable spaces S and T are Borel isomorphic if there exists a bijection, blah, 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 such that both F and F inverse are, yeah, bijection is important here, such, yeah, I think it's important. What if you didn't have a bijection? Is it possible that it could be so... Because what you think of is like, if I have a bijection between A and, let's say, just 0 to 1/2, that should be good enough. If it's bijective to any space that's bijective. That's an interesting question. What subsets? Well, someone certainly looked at this as of R are homeomorphic to 0, 1. Probably just something like all the open balls or something. We show that every Polish space endowed with its Borel sigma field is Borel. Okay, so Polish space basically just means that it looks like it has the properties of the unit interval in a topological sense. Let's see what 6 says. Topological space is said to be Polish if it is separable and admits a complete metrization. I agree that the unit interval satisfies this. There's some weird things though. Zero to 1 is compact. So I guess the reals aren't a Polish space? Yeah, this is weird. Okay, let's just keep moving. Polish and Borel spaces. For any Polish space S, we have one S is homeomorphic to a Borel set. Measurable space S is said to be Borel if it is isomorphic to a Borel set in 0, 1. Okay, that makes sense. Okay, so it doesn't even have to be connected. You could have the real line, something like this, and that would indeed be a Borel measurable space, I guess is what you call that. Alrighty. Just one sec. Bit rate's not good enough. We'll see how this turns out. Theorem 1.8, for any Polish space S, we have that this seems like it should be a gnarly proof. And indeed, it's not. It's decently long here. It's a surprising, non-obvious result there. Polish and Borel spaces. Borel isomorphic. Okay, Borel space. Borel measurable space, Borel space. That's fine. Okay, for any Polish space S, we have that S is homeomorphic to a Borel set in 0, 1 to infinity. What is a Borel set? Ah, an element of the sigma algebra. Did they bother to define this? Elements of are called Borel sets. Yeah, I should have some faith in this. So elements B sub S are Borel sets, elements of the sigma algebra induced by the topology. Does that look fine on stream? Yeah. Okay. Streams bitrate is. Recommend that you use a stream bitrate of 6800. Huh. Surprised it's that slow. All right. Proof 1. Fix a complete metric in S. Okay. Done. Homeomorphic. Borel isomorphic. So we say that measurable spaces are Borel isomorphic if there exists a bijection, such that both are measurable. I see. Okay, so in order for it to be continuous, this means that the bijection is continuous in both directions. And we need the space to be funkier. If it's Borel isomorphic, we can get less funky because this requirement is weaker. All right, so I'm at theorem 1.8 now. So, mess with my OBS thing here real quick. Okay. Is Borel isomorphic to, okay, fix a complete metric row in S. I don't know if we'll ever need this proof, but it's sufficiently surprising to me that maybe I should just learn it. Sorry, I keep changing the gain on my mic. Still trying to figure this all out. All right, so we fix a complete metric row in S. We may assume that row is less than or equal to 1. That's surprising. Otherwise, we can replace rho by the equivalent metric, min of rho and 1, which is again complete. I mean, yeah. Why is that complete? I see. Because if you have some convergent sequence, it'll be convergent in that space. Huh. That's weird. That's weird. It's weird that it's... So metric has to satisfy rho x sub y is equal to rho yx. That holds for this weird one, clearly. Rho of x is equal to 0. That clearly holds. I think the third one is just the triangle inequality. Metric space into Wikipedia. Positivity, yeah, sure. That's, ignore that one. Triangle inequality. So rho of xy plus rho yz greater than or equal to rho of yz. So I guess I would just go through the different cases. If all three of these are greater than 1, if all three of these 1, 2, 3 are all greater than 1, this holds for that max thing. If this one is greater than 1, but these two aren't, it just makes this one smaller, so we're good. I'm just going to assume the rest of it works out. Okay, fix a complete metric rho and s. We may assume that rho is less than or equal to 1. Otherwise, we can... That is interesting. That's a fun trick. I'm sure I'll never have a use for it in my entire life, but that's a neat one to see. Since S is separable, we may choose a dense sequence x1 through xn. Yep. Then the mapping. This is just a set of distances between rho and that dense set. Defines a homeomorphic embedding of S. I do think defines a homeomorphic embedding of S into the compact space K0, 1 to infinity. So I can see how this turns X into a I can see how this turns X. I don't get why this is homeomorphic. To the compact space. All right, so we can turn this into a collection of why is this space compact? That's weird to me. so maybe it's worth, I see. So it's probably worth thinking about the topology on 0, 1. I guess it's just induced from the product topology. 0, 1 to infinity. So this is just equal to, we'll just call this u. U cross u cross u. And then you get some open sets in here, u, a couple of other open sets. It's all but finitely many of these sets are open. This is a weird one. And the mapping X to, I just don't think that should be a set. I think it should be a sequence here. Defines a homeomorphic embedding of S into the compact space. It surprises me that this is compact. Compact means that any infinite cover has a finite subcover. Yeah, I mean, I guess that's fine. That's a weird question, but yeah, I would need to think about that. And we may regard S as a subset of K. I don't know if it's is it homeomorphic? Is that right? Homeomorphism of topological is 1-to-1 continuous inverse function is continuous. I don't know how much time I want to spend struggling on this. Defines a homeomorphic embedding of S into the compact space of this. Compact I can believe. Homeomorphic. I guess embedding, topological embedding just means it's a subset. Let's see here. Topological embedding. Yeah, it's got to just be a subset. It would be weird if it wasn't. Okay. So, space K is compact, and we've managed to poop X into it. We may regard S as a subset of K. Yeah. In K, we introduce the metric distance it's basically we just go through each index just sort of gets smaller and smaller. All right, and we define S bar as the closure of S and K. Sure, whatever. Writing P sub X epsilon sub P rho as the rho diameter ball D ball is the rho diameter of the D ball. Y and S. Yeah, so S is this dense subset. S we define I haven't read a trippy one like this in a while. I've just been sticking to more normal looking measure theory. All right, so writing this for the rho diameter D ball. So Y in S is this. Ah, I see. So S is the entire space. Fine. Okay. Define S bar as a closure of S and K. Hard to imagine what that looks like, but let's roll with it. So this metric basically, I mean, it's just the ball. I see. So you send an element, so you can take S into X. We send it over using that function. The metric might be different though. Well, let's just keep continuing. Let's just power through and see if something happens in my brain. And Y is X, then in X we define U sub n to be X and the closure of that thing such that, okay. Such that the ball is kind of small. Okay. Put GNR open in X sense. This is a funky one. I don't think I'll ever need this. I'm gonna skip that one, I think. For any Borel space S, we may define a localizing sequence. So some collection of nested subsets. And we say that a set B in S is bounded if, okay. If B is a subset, interesting. That's a weird one. So this is, instead of a metric, you can have a localizing sequence. Yeah, so this has to do with typically you say a set is bounded if well, for all y in this space, this is bounded by some constant. This is for all y in your set. But instead what we can do is make a localizing sequence. God, maybe, yeah. So localizing sequence for boundedness in R2 would look something like this. And indeed that would work, That's weird. And we say that a set B is bounded if B is in S sub n for some of them, yeah. So if your set is bounded, yeah, eventually it'll be in one of these circles. That's interesting. ring of bounded sets will be noted by S hat. Okay, the ring of bounded sets B in S will be noted by S hat. Good, fair enough. If rho is a metric generating S, we may choose S to consist of all rho bounded sets. Fine. In locally compact spaces, locally compact, what does that mean? I think any point is contained in a compact set. It's kind of interesting how, like, every point, they are all equivalent if X is a Hausdorff space. Right. So Hausdorff space means for any 2 points, X, Y, you can find 2 open sets that don't intersect. That contain each of the points. I don't think I've ever worked in a non-Hausdorff space. Every point in X has a compact neighborhood. Yeah, so, I mean, pretty simple. Probably call it after this. In locally compact spaces S, we may choose the class to be, okay. We may choose S to be consist of all rho bounded sets. So indeed, does not even need to be bounded sets which are measurable. Okay. Locally compact spaces S, we may choose S to be the set of classes P sub S with compact closure. And locally compact spaces. It's hard to see where this is going. By a dissection system in S, we mean a nested sequence of countable partitions such that for any, I don't like this, so N, for any fixed N, every bounded set is covered by finitely many of these. Topological spaces, we require in addition that whenever S is an element of G, is an element of an open set, we have that it contains some element of the dissection system. A class C, God man, these are some very particular properties. A class C of S is said to be, so class S means a collection of subsets. Class C of S is said to be dissecting if every open set in G is a countable union of sets in C. So basically, every open set can be represented. It's a bit like a separable space. Every set P is covered by finitely many. Any compact, okay. So it could be bizarre, but some part of it's got to be nice. To state the next result, we note that any collection of functions f make it xi, I defines a mapping. F to so SI is not defined here. I don't know. This is just like infinite product function as far as I can tell. F of omega is equal to the set f of I such that I is in I. We may relate the measurability of f to that of coordinate mappings. Okay, I think that's enough for today. Hopefully this doesn't look too bad. Thank you for watching, nobody. Bye-bye.